Let's look at our structural analysis. Structural analysis is a kind of old subject. All right, it has been there for many. Actually, one of the first things in engineering, civil engineering, is structures. Eiffel Tower, and good example. Even like that. That's that type of stuff. So, so the chapters here are the first chapter, second chapter, third chapter are very important. You should really understand this, very well. The first 1, 2, 3, 4 is for a bigger branch. The first is trusses, all these highway trusses or building trusses, so on and so forth. And the other is there are some ways of doing this. Also, because the subject is very old subject, so there are actually many methods. All right, many methods developed overall. Some are no good now, because you see the computers came in only about 50 years ago. I started to work with computers when I was at the University of Illinois. I developed a lot of computer programs for ILIAC computer. But now, in a matter of 50 years, the whole world is using computers. Even little kid, I'm a 3-year-old kid. She already has a cell phone. They know what to do with this. I don't have a cell phone. I don't use it. But I think maybe I'm an exception, because I'm always in my office, so I really don't use it. But even little children now know computers. So what is really happening is, if I look back at the system, in another 5 years, would you solve any of these problems by hand? Absolutely not, because you just can't afford it. Suppose you sit down and I give you a truss, you take 8 hours to do a truss problem, calculations and all that stuff. Nobody will ever ask you to do that. If they ask you, the company will go broke. So what is now happening is, so the computers will take over. It's very unfortunately, civil engineering is going in the other direction. It's not using computers. For example, one of the very big fields is earthquake engineering. All right, this is Southern California, Northern California, and the West Coast as a whole, earthquake prone, because the United States on the western side is a continental plate, and next to it is the Pacific plate, the Earth thing. So the Pacific plate is moving north, relatively kind of north-south motion. So these big plates will suddenly break, because this movement gets arrested for a while, maybe 100 years or something. The last big earthquake was in 1933. We call Long Beach earthquake. It's really not a Long Beach earthquake. It's Newport Beach. The earthquake epicenter happens to be in the Newport Beach area. But at the time, 1933, probably there was no Newport Beach, so they call it the Long Beach earthquake. Very famous. Lot of damage in those days, and then a lot of masonry buildings. Buildings are built with masonry. So many buildings fell down. School buildings fell down, and then that's when this earthquake issue became very important. So California was the first one to do something about how to design for structures. When you talk about structures, the civil engineering type of, not aeronautical. See, aeronautical is a very advanced advanced. Aircraft is going through the loads, aerodynamic loads and flying and many things. Very complicated. And where every material, also airplanes are very efficient structures, right? They don't have, civil engineering structures are very inefficient, right? Because civil engineering structures are coming from many thousands of years since human beings started building something. So, as far as the civil engineering structures are concerned, we have trusses, you have trusses, and we have beams. This is what you concentrate mostly on undergraduate, trusses and beams. And by the time you come back to frames, frames are really very important. This frame means, in some ways, this hollow space what we have, basically the walls on the roof, all right. But the walls, if the space is very long, you have to go to a frame, right? Because the walls cannot not only walls cannot. I don't know how Trump is going to build a wall between Mexico and the United States. It really doesn't make any sense. But I sent him a note too, I mean, why don't they put electronic fence rather than brick and wall, And not only, anyway, let's not get into politics. So the frames are very important, all right. All the high-rise buildings, there are no walls there, all right. The loads are from the slabs, and then the slabs go into the columns, and these are all the frames. For example, we have 2 or 3 high-rise buildings in the spectrum. They're not walls. They're frames. But of course, walls are also very important. You call wall as a shear wall, basically if it is resisting a lot of shear. In other words, a wall can resist vertical loads, that's normal wall. But also, especially the buildings carry on the slabs a lot of weight, and when the building shakes, the building becomes like a horizontal force. The floors become like a horizontal forces, and they come through the walls. And then we call them as a shear wall, because they're resisting shear. And then, of course, this is all civil engineering, only that much. But when once you go to, in real life, when you go to a 2D, this floor is a slab, right? This room you are sitting is a slab. But the slab, you don't even discuss slabs in undergraduate studies at all, because they are very complicated equations. And so, in other words, once you go from these simple structures to this, our base, we just don't have the analysis capability. But now, with the computers, we have all the analysis capability. It's very simple. So, I'm not going to practice, I'm not, in the practice, but if I'm practicing structures, you should become very well, get used to computer methods. There again, the computer methods are also there are not a lot of, public type. See, for example, aerospace companies, they use NASTRANs long time ago. It's a very huge program, NASTRAN. There's a public program. Probably Air Force has the license for that. But then many companies use the NASTRAN and develop, other programs for aerospace. Civil engineering also has some computer programs, but they're all in the private domain. So when things are in the private domain, how do you know the computer is doing a good job? That's what it's supposed to do. It gives some answer, but how do you know the answers are right? But luckily, we have now more than one program to do that. So I think if I am a practicing instructional engineer, and that will be, I have no computers, and then then I will do maybe not one computer program, maybe two, and do the analysis, because you don't know what the analysis. These private companies won't tell you how they are doing. All right, they give you an answer, but how did you get the answer? You know, it's the if they tell you all those, then you take over their companies. All right. Anyway, so the slabs and diaphragms are computable. Now what happens when once you have the structure, you apply the loads, all right. You apply the loads on the structure, and what loads you apply is depending upon where you are, and all the rules and regulations. You have to follow that. Apply the loads. When once you apply the loads, now you look at the structure. The external forces will create internal forces. All right. So the internal forces, this is like a column or just a member with a force of N or a P or S, whatever it is, axial force. It could be in a bending moment, right? Or it could be shearing force, or it could be also a torsion. But in civil engineering, we don't have much of torsion, because we sort of design the structures in such a way. Torsion is not we take care of some other way. But if you take airplanes, that's all torque, all right. So very, very important for Air Force. So NASTRAN is a very big computer program. So what happened? So in other words, first are the loads. The loads will create the forces. So this itself is a big step. Exactly how do you have some loads, some structure, what are the internal forces? After knowing the internal forces, what happens? The internal forces, suppose you have an axial force. This axial force, the internal force will be internal, not force, because force is so many kips and things like that, right? So many thousands of pounds. But the material has to withstand the force. That depends on the stress. In other words, how much force is going through. Suppose you take, that's called pounds per square inch, PSI, or kips per square inch. The stress. If you apply a force N, the stress will be sigma equal to P over A. It's a lot more complicated than P over A, because for P over A, that means this force N has to be applied exactly the centroid, so that all the fibers will move same, and then the stress is a thing. This is very important. Sigma equal to P over A. That's for axial stress. Bending moment, MC over I, sigma equal to MC over I. So that means what happens when a deformation looks like that, and the stress is MC over I. For the shearing force tau equal to VQ over IB, and the torsion TR over J. This, I think all of you should have had this long time ago in the strength of materials class, right? We'll come back to that. I'm just going overview. So what are the stresses? The codes have a limit on the stresses. You have to compute stress, and the code will tell you it can't exceed so much. For example, if you take steel 50 KSI is where it yields. The steel, there comes the material properties. So we have material properties. There is steel, there is concrete, there is masonry and timber, right? They all have different stress levels. The codes will specify all the ICC code, or right now the ASE, they specify what is there. But it is a torsion of the TR over J. When once, that means what happens? You have a structure, you have good internal forces, internal deformations, and then each one will extend or contract, right? Because it depends on the stresses. So if you take a truss, you have to compute the deflection of this, how much it is, and the codes will tell you can't have more than whatever the number is. So you have to find the displacements. We call displacements. There are limits on the displacement for the code.